Question 15. A company makes toys for children. Figure 5 shows the design for a solid toy that looks like a piece of cheese. The toy is modelled so that face ABC is a sector of a circle with radius R and centre A. Angle BAC is 0.8 radians. Faces ABC and DEF are congruent. Edges AD, CF and BE are perpendicular to the faces ABC and DEF. And edges AD, CF and BE have length H. Given that the volume of the toy is 240 centimetre cubed, show that the surface area of the toy, S centimetre squared, is given by S is equal to 0.8 R squared plus 1680 divided by R, making your method clear. Okay, now what I like to do, if I'm solving a question like this, I want to try and break it down into the smaller parts. So I'm going to start with surface area of this shape. And the surface area of this shape is not an easy one. So I like to use these diagrams here to help me keep track of what I'm looking at. But I know the surface area of this toy to be the surface area of the top and bottom. So that's the area of these sectors, A, B, C and D, E, F, of which there are 2 of them. It has the 2 faces which are rectangular. So I've got ADBE and ACDF. So there's 2 rectangle faces which are the same. And then finally it has a rectangular face on the front here, which I know to be the height multiplied by this sector arc length. But it is a rectangle. And so what I want to do is write down the formula for each of these faces. So the area of the sectors, the sector area ABC is half R squared theta, and theta in this case is 0.8. So simplifying this, my sector areas are 0.4 R squared. My rectangular faces on the front and back here are the height times the radius. That's just length times width of a rectangle. And I've got 2 of those. And then my rectangular face on the front here, or the curved rectangular face, is the height multiplied by the sector arc length, and arc length is R theta. So this is H times R, my theta in this case is 0.8. So that rectangular face has area H times 0.8 R. Now I've got these H values here. I don't have an H in the formula I'm given, so it would be nice if I can find H in terms of R. I am told that the volume of the toy is 240. So if we start to use volume, I can find a volume equation from my diagram. So since AD, CF and BE are perpendicular faces, then this is a prism. And so to find the volume of a prism, I take the area of the face and multiply it by the length. So in this case, that's the area of this sector, which we found to be 0.4 R squared, multiplied by the length. The length of this prism is H. So I have an equation for volume, and I'm told that the volume is 240. So I can rearrange my equation here. So if I take my volume of 240 and divide it by this 0.4 R squared, then I have an equation for H in terms of R. Now, we don't particularly like decimals in our fractions here, so we can simplify this to be 600 over R squared. So now I have something for H in terms of R. I can substitute that into these area equations that I've found to hopefully get something that looks like this. So I'm running out of space here. So let's bring together what we've found. So I know my surface area to be 2 lots of my sectors. I've found my sectors to be 0.4 R squared. So 2 lots of 0.4 R squared, plus 2 lots of my rectangle, which I've found to be HR, plus my rectangle BECF, which I've found to be H times 0.8 R. Now I've also found my height to be 600 over R squared, and now I can look at substituting this H value into these equations. And so 2 times 0.4r squared remains unchanged, but 2 times my height times r leaves me with 1200. It would be 1200r over r squared, and single r will cancel. And then h times 0.8r, again an r will cancel, and I'll be left with 480 over r. If I add these together and simplify, I do indeed get 0.8r squared plus 1680 over r, and that's the surface area of my toy S. Using algebraic differentiation, part B, find the value of r for which S has a stationary point. Well, let's start with S, and I've written my S as 0.8 r squared plus 1680 r to the minus 1. The reason I've written this like this is it makes the differentiation a little bit easier. So now I have my S written in a form I can differentiate simpler. My ds by dr then, multiply by the power and reduce the power by 1. 0.8 r squared becomes 1.6r, and then 1680 multiplied by minus 1 is minus 1680. Subtract 1 from this power, and this is r to the minus 2. Since I want the value when it is a stationary point, ds by dr will be equal to 0 when it is a stationary point. And so I can write 0 is equal to 1.6r minus 1680r to the minus 2. If we add the 1680r to the minus 2, then I can write 1.6r is equal to 1680r to the minus 2. I can now multiply both sides here by r squared to give me 1.6r cubed is equal to 1680. And now if I divide by 1.6, I've got r cubed is equal to 1050. Cube rooting both sides, I get r is equal to 10.16, and so on. Part C, prove by further differentiation that this value gives the minimum surface area of the toy. So I'm bringing my differentiated function from part B. So the first derivative, ds by dr, was 1.6r minus 1680r to the minus 2. I'm using further differentiation to show that this is a minimum surface area. So differentiating this again, I get d2s by dr squared. 1.6r differentiates to 1.6. 1680 or minus 1680 multiplied by minus 2 is positive 3360. Subtract 1 from the power, so that's then r to the minus 3. Now I know my r value at this point to be 10.16 and so on. If I substitute this value of r into my second derivative, I can use the actual value of r here. Remember, r was the cube root of 1050, so 10.16 and so on. And my d2s by dr squared then is 1.6 plus, and I'm going to write this as the fraction, 3360 over my answer, which is my 10.16, and that's cubed. And I get an answer of 24 over 5, or 4.8. Hopefully I've shown on a calculator that's 4.8. The important thing here is that that is positive. And since the second derivative is positive, this is then the minimum surface area. Remember, with second derivatives, a positive value denotes a minimum point, and a negative value would denote a maximum point.